The video will start in 5, 4, 3, 2, 1. Welcome back, cosmic explorers of the U.N.S.S. Phoenix XCS 337. Today, we're venturing into the strange and mind-bending realm of time and motion. It's well known that time dilation occurs at the speed of light, where time appears to slow down as an object approaches that ultimate speed limit. But what happens at the opposite extreme, when an object reaches zero velocity relative to the rest of the universe? Could time speed up, going by in a blink of an eye? Let's explore the fascinating relationship between speed, time, and relativity, as we unravel the mysteries of how motion, or the lack thereof, affects the passage of time in the cosmos. According to Einstein's theory of relativity, the closer an object's speed gets to the speed of light, the more time slows down for that object relative to an observer at rest. This effect, known as time dilation, means that time stretches out as an object approaches light speed. If an object could actually travel at the speed of light, something that's theoretically impossible for anything with mass, time would effectively come to a standstill for that object. Let's look at some real-world examples. Experiments with particles accelerated to near light speeds, such as in the Large Hadron Collider, have shown that these particles live much longer than they would at rest. Even atomic clocks flown on airplanes have demonstrated time dilation, where clocks on the moving planes tick slightly slower compared to those on the ground. The faster an object moves through space, the slower it experiences the passage of time. This effect becomes significant at relativistic speeds, those approaching the speed of light, but is negligible at the speeds we encounter in everyday life. Now, what about the opposite end of the spectrum, zero velocity? At zero velocity, an object is at complete rest relative to its surroundings. But in a universe where everything is in motion, planets orbiting stars, galaxies swirling through space, is achieving true zero velocity even possible? If we think about it in terms of relative motion, we need a reference frame to define what zero velocity means. Let's consider the cosmic microwave background, CMB, the oldest light in the universe. If an object could somehow be at rest with respect to the CMB, that would be as close as we could get to true zero velocity relative to the universe. So, would time appear to pass more quickly at zero velocity? Unlike time dilation at high speeds, the relationship between time and motion at very low velocities is much less dramatic. In fact, general relativity tells us that zero velocity does not inherently cause time to speed up. The passage of time remains relatively unchanged for an object at rest compared to one moving at sub-relativistic speeds. If you measure your speed relative to the cosmic microwave background, you would find that the Earth is moving at roughly 370 kilometers per second. While zero velocity doesn't inherently cause time to speed up, our perception of time can be influenced by perspective and relative motion. For example, consider a traveler moving at near light speeds who then comes to a stop relative to the Earth. They might perceive the world as moving much faster than during their high-speed journey due to time dilation effects. To the traveler, time on Earth would have seemed to speed up when they decelerated from near light speed back to rest. But for an observer who's always been moving slowly relative to the cosmic reference frame, there would be no noticeable speeding up of time. This highlights that time flows consistently unless relativistic speeds or strong gravitational fields are involved. While zero velocity itself doesn't speed up time, gravity does affect the flow of time. General relativity predicts that time passes more slowly in stronger gravitational fields. For an object at rest near a massive body, such as a black hole, time would indeed pass more slowly than for an object at rest in deep space far from any gravitational influences. The closer you are to a massive object, the more time slows down for you relative to an observer far from the source of gravity. However, if you were floating at zero velocity in the emptiness of intergalactic space, far from any massive objects, you would experience time at its fastest possible rate due to the lack of gravitational time dilation. In this scenario, being at rest in a region of very low gravity could be considered as experiencing time at normal speed. Gravitational time dilation is noticeable even on Earth. At higher altitudes, time runs slightly faster compared to sea level due to the weaker gravitational field. Riddle: I'm slow and still, yet I'm part of the flow. Time passes for me, though not too fast or slow. What am I? As we conclude our exploration of, if time stops at the speed of light, does that mean time goes by in a blink of an eye at zero velocity? We find that while time slows dramatically at the speed of light, it doesn't speed up at zero velocity. The flow of time is intricately connected to motion, gravity, and the cosmic reference frames that shape our understanding of the universe. Whether at rest or in motion, time's nature remains one of the most fascinating aspects of physics. It continually reminds us that our perception of reality is deeply connected to the way we move through space and time. Riddle answer: the flow of time. Question for you: if you could experience zero velocity in a part of the universe with almost no gravity, what would you do with the time you had? Would you spend it observing the cosmos, or would you focus on a personal project that requires deep concentration? Let us know in the comments. Cosmic Comic, Space Diner Delights, The Blink of an Eye Pie, Panel 1, an astronaut sits at a space diner and orders the blink of an eye pie. Panel 2, the alien waiter brings out a pie that appears to shimmer and vanish when you look away. Panel 3, the astronaut looks puzzled, where did it go? Panel 4, the waiter replies, it's a special kind of pie. It's only there when time flies. And thanks for watching.